This is going to be our first lecture for Module 7. This lecture we're going to go over residential service calculations as they apply to Article 220. So objectives for this lesson, we're going to use Table 220.12 to determine general lighting load. Use Table 220.42 to apply lighting demand factors to our general lighting load. Determine load requirements for fixed appliances. Use Table 220.54 to determine dryer loads. Use Table 220.55 to determine cooking equipment loads. And calculate the total load required to serve residential dwellings. So you may notice by our objectives, when we're dealing with Article 220 and dwelling calculations, we have a lot of different tables that we have to be able to use and know how to reference. We're going to be going over those in a lot of detail during this lecture. Make sure everybody knows how to use those tables. For definitions, appliance, fixed, is an appliance that is fastened or otherwise secured at a specific location. This will be important for one of our steps when we're doing our service calculation. Generally speaking, the way I like to think of a fixed appliance is any appliance that requires tools to remove. So in other words, if we think about a microwave just has a simple cord and plug attachment. You can unplug it from a receptacle and then just pick it up and move it. Same deal with a refrigerator. On the other hand, if we think about like a water heater is mechanically connected to the plumbing system via PVC piping usually, and usually it'll be hardwired from a non-fused disconnect using flexible metal conduit or MC cable, something to that effect. So essentially something you need tools in order to remove is how I like to think of a fixed in place appliance. And non-coincident, the fact or state of not coinciding, lack of coincidence. Where it applies to Article 220 with non-coincident, I usually think of this in terms of they will not be operating at the same time under any circumstance for any reason. In other words, it's essentially impossible for them to be operating at the same time, and that'll make more sense once we get to that step. So Article 220 covers branch circuit, feeder, and service calculations. With the lecture name, we're going to be looking at dwelling calculations. This is going to be another lecture similar to our motor load calculations, where instead of just going through the article, we're going to be bouncing around a lot and looking at different steps in order to get a final calculation and do that in the most logical and easiest way possible. So when we're doing a full dwelling calculation, and when I say a dwelling calculation, the objective here is to figure out how big of a service do we need to supply a dwelling unit. In other words, how much power do we need to supply that home? We can break this type of calculation down into 9 steps. Our first step is going to be looking at Table 220.12, which is our general lighting load. Our second step is going to be looking at Table 220.52, or just Article 220.52 for our small appliance circuits. Step 3, we're going to be looking at Table 220.42 for our lighting demand factors. Step 4, we're going to look at 220.60, which is our non-coincident loads, and as I said, it would make more sense. The main one we deal with for that step is AC versus heat. You're never going to be running the AC in your home the same time you're running your heat. Step 5, 220.53 are fixed appliance loads. Step 6, 220.54 are dryer loads. Step 7, 220.55 cooking equipment loads. Step 8, 220.50 are motor loads. And step 9, we're going to calculate the total load based on the sum of our other steps. So here we have an example dwelling. It's going to be 2,500 square feet. It's going to have 8 kW heat unit and a 240 volt 5 horsepower single phase AC unit, 4 fixed in place appliances, one 1,500 watt water heater, a quarter horse 120 volt disposal, 1,000 watt hot tub, and another 15 amp 120 volt appliance, a 4,500 watt dryer, and a 14 kW cooking unit, whether it be a range, oven, whatever may have you. So I recommend you take a second to either write this information down or just take a screen capture of this screen, because we're going to be referencing this information as we go through our steps, and we won't be going back to it after we leave it. So I'm going to give just a second to make sure everybody can get this. And we're going to move on to our step 1, our general lighting load. So for our general lighting load, we're going to be going to table 220.12, which, and on our next slide, we'll be taking a look at that table. 220.12 essentially tells us to take the square foot size of the dwelling and multiply it by a volt amp amount. And for the sake of Article 220 of the code, it's important to keep in mind we're going to be using the term volt amp a lot. You can, once again, for the purposes of Article 220, think of a volt amp as the same thing as a watt. So essentially, we're going to be multiplying the square foot by a watt number. So looking at table 220.12 here, our general lighting loads by occupancy. We see on the left-hand column the type of occupancy, and keep in mind an occupancy is just a word for what kind of building is it. Now on the right-hand side here on that column we have the unit load, and we have that in volt amps in meter square and in feet square. We're going to be using the feet square column. So since we're doing a dwelling calculation on our type of occupancy, we're just going to go down till we find dwelling unit, and then straight across till we're under the volt amps per foot squared, and we see a 3. In other words, what we're going to be doing for our step number 1 is taking the square foot of the dwelling unit and multiplying it by 3 volt amps per square foot. And that's all we're going to be doing for step number 1. So for step number 1, we come out to 7,500 volt amps total. We had a 2,500 square foot dwelling, 3 volt amps per square foot, 7,500 square feet, or 7,500 volt amps, sorry. Moving on to step number 2, our small appliance branch circuits. 220.52A requires 1,500 volt amps for each circuit required by 210.11C1. And in 210.11C1, we have a total of 2 circuits required. 220.52B requires 1,500 volt amps for each circuit required by 210.11C2. And 210.11C2 requires a total of 1 circuit. So in other words, we have 3 total circuits at 1,500 volt amps each for step number 2. So we have a total of 4,500 volt amps for step number 2. And that's always going to be the same for step number 2 anytime you're doing a dwelling calculation. If you're doing the entire calculation and walking through it like this, step number 2 will always be 4,500 volt amps. Now for step number 3, our lighting demand factors. Table 220.42 allows demand factors to be applied to the values calculated in steps 1 and 2. So in other words, for the 7,500 volt amps we calculate in step 1 and the 4,500 volt amps we calculate in step 2, we can apply a demand factor to those to reduce those numbers to a smaller one. So what we're going to do is we're going to take our first 3,000 volt amps of that total amount at 100% of the value. So for our 7,500 volt amps and our 4,500 volt amps, that comes out to a total of 12,000 volt amps. So of that 12,000, we're going to take 3,000 from it and rate it at 100%. Then, for whatever we have left from 3,001 volt amps to 120,000 volt amps, we're going to be rating that at 35%. So since we already pulled 3,000 from our 12,000, that left us with 9,000 volt amps. So for our step number 2, we're going to be taking 35% of that, which would come out to 3,150 volt amps. And then if we have anything over 120,000 volts, we would be taking that at 25%. In our situation, we do not. And here is that table 220.42. I already kind of walked you through how to use it, but once again, on the left-hand column, you have the type of occupancy. We're in a dwelling unit. And you can essentially see the information I told you. First 3,000 at 100%, 3,001 to 120,000 at 35%, and remainder over 120,000 at 25%. So, as I said, for step 3 here, we took our first 3,000 at 100%. We took the remaining 9,000 volt amps at 35%, which equaled 3,150. When we add those two numbers back together, that gives us a total of 6,150 volt amps for step number 3. Now you may notice that I have grayed out steps number 1 and 2 at this point. That's because we're no longer going to be using those steps for the calculation in any way, shape, or form. Step number 3 replaces 1 and 2. So they are no longer, those numbers are no longer going to be used. We only care about step number 3 now. Moving on to step number 4, our AC versus our heat. 220.60 allows non-coincident loads to be compared, and the larger of the two used for our calculation or our load amount. Most often this will include the heat and AC units. The majority, pretty much every dwelling built in North America, or America specifically, currently is going to have both heating and air conditioning in it. And obviously you're not going to be running your heat unit at the same time you would your AC unit. And keep in mind, this doesn't apply to, small space heaters or bathroom heaters, things like this. We're talking about whole house heat and air units. So for this calculation, we had an 8 kW heat unit, which is how heat units will typically be displayed. A lot of times for AC, though, as we had in this situation, we have a motor load amount. We don't know what the kW is. So in order to establish which of those is going to be the bigger of the two, we would have to convert them to like terms. Now, we don't really have any way to convert a kilowatt amount to a motor size, so we don't have any choice but to convert that motor into a kilowatt size. In order to do that, it being a 240 volt single phase motor, all we would have to do from our motor load calculations, if you recall, is go to table 430.248, find the FLC of the motor. Everyone should be familiar with Ohm's law at this point. When we have amperage and we have voltage, we just multiply those together. That gives us wattage. And we just divide wattage by 1,000 to get our kW. So in this specific situation, once we've done that and compared how big the AC comes out, the heat is going to be the larger of the two. So we're going to be carrying the heat number or value for step number 4 since it was the bigger of the two. We don't care about the AC load. Since logically, if the service is sized large enough to carry the bigger of the two and only one of them is ever going to be running at one given moment, if we have enough service for the big one, we can also run the little one when it's necessary. Step number 5 are fixed appliances. 220.53 allows a 75% demand factor to be applied to 4 or more fixed in place appliances. We had a list of fixed in place appliances at the beginning of this. Once again, depending on what you're given, whether it be an amperage amount or a voltage amount, you may have to use some Ohm's law in order to calculate a watt amount or a volt amp amount for those. If you're given a motor load, such as your disposal in this situation, you may have to go back to table 430.248 or table 430.250 in order to find the FLC of that motor and then use your Ohm's law to get your watt amount. But once you've converted all of them to wattage, all you have to do is add them together and then find 75% of that total amount, and that's going to be your step 5 amount. And it's important to note, and remember, we can only do this if we have 4 or more fixed in place appliances. If we only have 3 or less than 3, we have to rate them at 100% of the appliance load. So for step number 5, once we converted everything to a wattage, added them together, and then found 75%, we come out with 3,747 volt amps for step number 5. Moving on to step number 6. 220.54 requires a minimum of 5 kW be included for dryers or the nameplate, whichever is bigger. Now in our situation, we had a 4.5 or 4,500 watt dryer. Now, as we see here with 220.54, since that number is smaller than 5 kW, that means we're going to be including 5 kW for our dryer amount for step number 6. And it's worth noting that table 220.54 lists the demand factors for 5 or more dryers. And the reason I say 5 or more here is because if you only have 1 to 4 dryers, you're still going to be rating each of them at 100%. It's only once we hit 5 dryers in one dwelling that we can apply a demand factor to those. And per 220.61, our neutral conductor size may be reduced to 70%. In other words, if we carry 5 kW load for our ungrounded conductors in step number 6, we're allowed to carry 70% of that 5 kW for our grounded conductor or neutral conductor load for this step. I'm not going to walk you all through doing the calculation that way. It's a little bit more advanced, and a lot of times, unless you have multiple dryers or multiple ranges, you usually end up having to use the same size neutral conductor anyway. But I did want to make sure that everybody was aware of that if they ran into it. So for calculation, step number 6, once again, since we had a 4,500 kW dryer per 220.54, that means we automatically have to rate that at 5 kW or 5,000 volt amps. Step number 7 for cooking equipment. Table 220.55 lists demand ratings for cooking equipment. We are always going to be using column C of this table unless our question specifically tells us to use a different column. We'll always use column C in this table. And we have a note here. If you look at the bottom of the table, you'll see several notes. I'm only going to be addressing note 1 because it's the one you'll most often be using. And once you have a basic understanding of how to use this table and how to apply the note 1, if you need to use one of the other notes, it's very easy to take that base knowledge and roll it into the other steps. Note 1 tells us for cooking equipment larger than 12 kW, we have to increase the column C value by 5% for each kilowatt that we are over 12%. So looking at table 220.55 here, once you understand that you're only going to be using column C and you understand that note 1, it's a pretty straightforward table. So on the left-hand column, we have a number of appliances, and then in column C, we have a maximum demand for ranges not over 12 kW. So say we have one 10 kW range. We're going to go to our number of appliances, and we see one appliance. Once again, if we go straight across to column C, we get 8. And as the table tells us, this is in kW, so we have 8 kW. In other words, for a 10 kW range, we're only required to include 8 kW of load. Now, on the flip of that, however, if we had a 5 kW range, we would still have to include at least 8 kW of load in the equation. Once again, if we had two 10 kW ranges, we go to our number 2 of appliances and go straight across, and we get an 11 kW. In other words, for two 10 kW ranges, we only have to include 11 kW of load. Now for our note 1, as it told us, if we have a range that is larger than 10 kW, we have to increase this column C amount by 5% per kW. Now, if I recall, we had a 14 kW range in this equation. That would mean that we are 2 kW over 12 kW. 14 minus 12 equals 2. So for each of those KWs, we have to increase the column C amount by 5%, which means since we're increasing it by 5% 2 times, that means 10%. So for a 14 kW range, we would have to increase our column C amount by 10%. If it were a 15 kW range, we would be 3 kW over, so we would have to increase our column C value by 15 kW. Step number 7, we did have a 14 kW range, so for our 8 kW for one appliance, we increase that by 10%, and we come out to 8,800 volt amps. And looking at step number 8, which is our semi-final step here, we're almost to the finish line, we have a motor load increase. Now this is the step of every one of the steps in this equation I think I see people mess up the most, because there are two really easy ways to mess this step up when you're doing it. So I'm going to try to walk through it very slowly and methodically here to make sure everyone understands what these confusing parts are. So Article 220 or Section 220.50 requires that motor loads for a dwelling meet the requirements of Articles 430.22, 24, 25, and 26. For circuits, including services supplying multiple motors, the largest motor must be increased by 25%. If you recall, back when we were doing our motor load calculations, for both the branch circuit conductors, well, our branch circuit conductors had to be rated at 125% of the motor FLC. And for feeder circuit conductors supplying multiple motors, they had to be rated at 125% of the largest motor. So that's the idea that we're going to be looking for in step number 8, is that our service needs to be sized at least 125% of the largest motor. Now, the first where I see people mess up a lot is, since you need to pick out the largest motor, they'll go back through the equation that we've done and try to find where the largest motor was. And more often than not, it'll be your AC load. However, if back in step number 4, you didn't use the AC and instead you used the heat, we know we don't care about the AC motor anymore. It's been removed from the calculation here. In other words, even if it was the largest motor, if we didn't use it in step 4, we're not going to count it in step 8 either. So we have to find the next largest motor. Now for us, in our particular equation or calculation here, the only other motor that we had besides the AC was our quarter horse 120 volt garbage disposal. So that would be the motor that we would use in step number 8 for this. Now this is where I see the second place that a lot of people mess up on this calculation. So we look at our answer here for step number 8, we get 174 volt amps. Now if you paused and did that calculation ahead of me, or you pause now and do that calculation, you may initially be a little bit confused, because this is not 125% of the FLC of that quarter horse 120 volt motor. What you have to keep in mind, and what I see people get confused on a lot, is that we already used 100% of that motor back in step number 5 for our fixed in place appliance load. So for step number 8, all we technically need is the additional 25%. In other words, if you add the load that we had in step number 5 for that disposal and the load that we added in step number 8 for the disposal together, you end up with a total of 125% of the load. And another thing that can confuse people is the 75% derating factor that we applied in step number 5. So technically, you could argue that we only have 75% of the load in step number 5 and not 100%. However, in the context of the code, that 75% is equivalent to the 100% due to it being a demand factor. So even though technically we only have 75% in as far as the code's concerned, we have 100% of the required amount of load in step number 5. So once again, we only need the additional 25% for step number 8. Now, wrapping things up here with step number 9, this is kind of where we just bring everything together and size everything. This is the fun step where we finally get to see kind of the fruit of our labor here. For step number 5, we're going to add the volt amp amount that we calculated in steps 3 through 8 together. Remember, we don't count 1 and 2 anymore. To find the total volt amps required for the dwelling. So once we add all those values together, we end up with 31,871 volt amps that we need to have available for this dwelling in order to run everything that's going to be in it. Next, we need to actually figure out what size service this is going to be. For those of you who have ever worked on a service or been in Lowe's or Home Depot and seen where they have service panels or meters for sale, they're sized in amperage. So in other words, we're going to have to convert this volt amp to a amperage amount we can use. So in order to do that, in order to find our overcurrent protective device, in other words our main breaker size, we're going to divide that total volt amp amount by our line voltage and go to the next larger standard size back in table 240.6a. Once again, from our motor load calculations, when we were sizing our branch and feeder overcurrent protective devices. Now, I see a lot of people get confused here as well because we do have the general rule when we learned in motor calculations and back when we studied Article 240 that branch circuits go up to the next higher size overcurrent protective device and feeder circuits go down to the next smaller size. What you have to keep in mind here is this isn't a feeder, though, because I see a lot of people try to go down to the next size. This is not a feeder, this is a service, and that rule does not apply to services. For services, we have to have at least the amount of amps and volt amps that we calculated during these steps. So we don't have any choice except to go up to the next larger size. So for our situation, we take our 31,871 volt amps and divide it by our 240 volt line voltage, which is standard single phase line voltage in America, and that comes out to 132.80 amps. Looking at table 240.6a, we see the next larger standard size from that is going to be 150 amps, meaning this is going to be a 150 amp service. Next, to size our current carrying conductors for the service, we of course would be going to 310.15b16 to pick out a wire size, and since we're over 100 amps or for a service, we're going to be using our 75 degrees Celsius column. However, for dwelling services, we have a special note back in 310.15b7, which tells us that we're only required to size those conductors to 83% of our overcurrent protective device. So instead of having to have conductors big enough for 150 amps, we only need them to be at 83% of that, which, as we can see here, 150 times 83% is equal to 124.5 amps. And the smallest the smallest copper conductor that we can use that's equivalent to at least 124.5 amps is going to be a number 1 copper conductor. So in other words, we're going to have a 150 amp service that we're going to be supplying using number 1 copper conductors. And this is going to conclude our first lecture for Module 7. In our next session, we're going to be going over commercial service calculation.